Okay, let me continue with a theorem about the error bound for the Lagrange interpolating polynomial. We know that when we interpolate a function like f of x with a polynomial of degree n, we call it Pnx. We know that there is an error between the value of, for example, f of x0 and Pn of x0. There is an error. An error will appear here. Okay? Now, we want to compute a bound, an upper bound, in fact, for this error. To this end, we have a theorem here. Suppose that x0, x1, 2, xn be distinct numbers in the interval a and b. Okay? It means that a equal to x0 less x1 less x2 less xn equal to b. And suppose that f be a function in Cn plus 1 over the interval a and b. It means that f and the derivative of f until the order of n plus 1 are exist and continues on the interval a and b. Then for each x in the interval a and b, there is a number like xi of x. Xi of x means that xi is depend on x. Okay? Between x0, x1 to xn, in fact, it's in the interval a and b, and hence in a and b, there exists such that we can write f of x equal to p of x. This is the function, this is the interpolating polynomial, okay, plus this term. What's this term? This term is exactly the error of p of x. What's this? This is the derivative of order n plus 1 at xi of x over n plus 1 factorial times this multiplication, in fact. Okay? We can call it pi of x minus xi for I equal to 0 to n. So we can write this formula a little easier. Now, we want to prove this theorem. For the proof, we note that if x be equal to xk for any k equal to 0, 1 to n, then what happened? Suppose that x equal to xk. So f of xk, we can write f of xk equal to p of xk. And if you have a look here, because we have x minus x0 to x minus xn, if x be equal to xk, one of these parentheses will be 0, and so all of this term will be 0 and just remain this equality. Okay, so this equality happened, and we can choose xk arbitrarily in the interval a and b, and in fact the equation is true. So we have to let that x not equal to xk for all k equal to 0, 1 to n, and we define a function g. Okay, a function g with the variable t in the interval a and b by this relation. Okay, we define g of t equal to f of t minus p of t minus f of x minus p of x times these terms. In fact, we can write this term in the compact form like this. Okay, so g of t equal to f of t minus p of t minus f of x minus p of x times pi I equal to 0 to n t minus xi over x minus xi. Okay, so since f is continuous on the interval a and b, and the derivative of f up to order n plus 1 are continuous as exist on the interval a and b, and also we know that p is belong to c infinity of a and b. It means that p is infinitely times in fact we can derivative p infinite on the interval a and b. So g function of g is belong to cn plus 1 a and b, because f and p are both belong to cn plus 1 over a and b. Now if we consider t equal to tk, t equal to xk, so we get g of xk equal to f of xk minus p of xk minus f of x minus p of x times this equality. We know that f of xk minus p of xk by this inequality for k, for x of x equal to xk, are equal, so this term is 0. Okay, and here if we consider x equal to xk, we know that in this pi, in somewhere I will be equal to xk, and 0 will appear in the nominator, so all this pi will be 0 and this will be 0, and we can conclude that g of xk is equal to 0. So in fact g of t has n plus 1 zeros, okay, x0, x1 to xn. Now you can consider g of x. In fact, you suppose that t is equal to x, so g of x equal to f of x minus p of x, we can write it here, and f of x minus p of x over this one, and we know that this term will be 1, so it just remains f of x minus p of x minus f of x minus p of x, and this will be 0. So we know that g has n plus 1 0 here from these points, and another one when we choose t equal to x. So totally g has n plus 2 distinct zeros, x0, x1 to xn. And now we know that by the generalized Rolle's theorem, we know that there exists a c in the interval a and b, okay, such that the derivative of g of order n plus 1 of c will be 0. So you can take n plus 1th order derivative from this equality. So we get the derivative of order n plus 1 at t minus pn plus 1 at t, and so on. Okay, so we get something like this. We know that this will be 0 by this one. Okay, so we can get fn plus 1 c minus pn plus 1 c minus fx minus px d n plus 1 to dt n plus 1 of this pi, in fact. Now p is a polynomial of degree at most n, so the derivative of order pn plus 1 of p will be 0. Okay, so this one will be 0. Okay, now it remains we compute this derivative. For this derivative we can move, in fact, the pi of the denominator out, and we can write this to this form: 1 over pi x minus xi pi t minus xi. And we know that in this pi from 0 to n, we know that the t of the in fact the degree of n plus 1 will appear in this polynomial. So the derivative of order n of this polynomial is 1, and a coefficient of 1 over p times pi x minus xi will appear here. So we have n plus 1 here, n plus 1 factorial over this pi. Okay, it's you can conclude this very easy if you just write in fact this parenthesis in a polynomial form. In fact, let me show you something. For example, if we have pi x minus xi, I equal to 0 to 2, here you will have x squared plus something. Okay, x squared plus x of order 3, plus something. And if you take derivative of order n plus 1, you will get 3 factorial. And in the same way, you can get n plus 1 factorial here. Okay, now you consider this derivative as this form in this formula. So finally, you will get 0 equal to fn plus 1 xi minus 0. This was in fact pn plus 1 at x, and something like this. And if you move fn plus, and if you compute f of x from this equality, you can get f, let me write it for you, f of x minus p of x, okay, equal to fn plus 1 xi, okay. We move this one here and this one here, yeah, times pi I equal to 0 to n x minus xi over n plus 1 factorial. Okay, and if we move minus p of x to the right hand side, we will get this equality, and it's in fact proved the desired result for us. In fact, this is the desired result. So the proof of the theorem is finished here, and we have nothing more to say about this theorem. Now let me show you an example here, and how can I want to show you how can we use this theorem. In the example in the previous lecture, we found the second, in fact, Lagrange polynomial for f of x equal to 1 over x on the interval 2 and 4, using by this node 2, 2.75, and 4. Okay, now we want to find an upper bound for this polynomial, interpolating polynomial. Okay, we know that f of x equal to 1 over x. Okay, so f prime of x is minus x to the power of minus 2, and f double prime is 2x to the power of minus 3, and f triple prime is in fact minus 6 x to the power of minus 4. So by the as a consequence of the previous theorem, in fact we have to compute f triple prime at xi of x over 3 factorial times this one. Okay, and if you put instead of f triple prime minus 6x to the power of minus 4, and you put xi of x, you can get minus xi of x to the power of minus 4. 3 factorial with minus 6 cancel, and just remain this term. And also put instead of x0, x1, and x2, 2.75, and 4 here. And we know that this is true for xi of x in the interval 2 and 4. We know that the maximum value of xi of x to the power of minus 4 in the interval 2 to 4 is 2 to the power of minus 4, and it's 1 over 16. Okay, and we now need to determine the maximum value of this in fact polynomial in the interval. For finding the maximum value of g of x over interval 2 and 4, we have to derivative of g of x. With derivative of this d of x, in fact, it will be 3x squared minus 35 over 2x plus 49 over 2, and we can write this in fact polynomial to this form, and we can find two zeros for this one. One is x equal to 7 over 3, and the other one x will be equal to 7 over 2. Okay, this one and this one. And if you compute the value of g of x at this point, g of 7 over 3 is 25 over 108, and for x equal to 2 is g of 7 over 2 is minus 9 over 16. And we know that the absolute value between these two, this one is greater, the absolute value of this one is greater. Okay, so the maximum error will be f triple prime of c of x over 3 factorial times this in fact parentheses, and we know that this absolute value is less or equal 9 over 16, and if you put it here, you can put it here. Okay, this absolute value, and also we know that f triple prime of c of x was less or equal here 1 over 16. So 1 over 16 here and minus 9 over 16 here, and in fact the upper bound will be this value, and it's all. So by this theorem we can find the upper bound for the in fact interpolating polynomial that we have found with Lagrange polynomials. So please follow me and subscribe my channel and wait for the next lectures.